life.
99 FM. Do the work.
The vertical columns are called groups. The horizontal rows are called periods. All right. We are going to have a look at the different groups and general tendencies within groups. Remember when we did SPD notation, we can differentiate S block elements, P block elements, D and F block elements. All right. The group of metals on this periodic table that are printed dark green in color are commonly known as the transition metals. And we'll have a look at the properties of metals when we get there. Those are the lanthanides and actinides. We don't normally work with them except for uranium that is used as a fuel in nuclear power reactors. I think I did, yes. Okay. All right. If you look in your textbooks there on page 40, you will see there are the first few bulleted points. They say group 1 and 2 metals are called alkali metals. Group 1 is the alkali metals. So group 1 is group 2 is known as the alkali earth. Metals. We don't bother with the names of the group 3s and the group 4 elements and the group 5 elements, group 6 elements. Group 7 elements are known as the halogens, and then just remember what is a halide. Yes, it's in the compound form. Okay, usually the ionic halogen. Okay. They talk about the transition metals that lie between group 2 and group 3. They form a unique group of metals, slightly different from those of group 1 and 2. Remember, metals are shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. And then we find that the difference between the group 1 and 2 metals, they are less dense, they are fairly light metals, and they are fairly soft metals. Group 1 and 2 metals are less dense, they are soft. Many of them float on water. They are soft, so they aren't high, they don't have high densities. Okay? We find that the transition metals, they usually form colored compounds, and they usually have higher densities with higher melting and boiling points. All right. Remember, the boiling point and melting point of mercury will not fit the pattern because it's a liquid at room temperature. Okay, I don't want to say more about the metals at this point. Then they say the group of metals on the right of the transition metals, these are called the B metals. On this periodic table, they're in light blue. We won't bother much with B metals, why they are called that or whatever. It's just take note, that's why they've got it colored in blue on that periodic table. Then the group of B metals, just B, capital letter B, B metals. Then the group of non-metals on the right of the periodic table, remember, there is a step going down through the periodic table. Below the step we have metals, above the step we have non-metals. In actual fact, the non-metals are only a few elements. Most of the elements are metals. And yes. Calcium is a metal. Remember, what confuses you is calcium carbonate or calcium salts. That is what your bones are made from. But it needs calcium. But you don't have calcium as a metal in your bone. You have calcium in the form of a salt in your bones and teeth. That's,
it's a compound in your
Yes. Okay.
So sy properties change.
Yeah.
Okay.
Yeah. Yes. Yeah. It's only a few that are non-metals. All right. If we go and have a look at the step, then we find that the elements lying on the step, like boron and aluminium, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, they very often have got properties that are slightly more vague. They aren't definite metals or definite non-metal properties. Carbon is one of them. It touches the step on the corner. Carbon, one of its crystalline structures in the form of graphite, does conduct electricity, while in general non-metals do not. Then we get silicon and germanium. Silicon is a non-metal, germanium is a metal, but they are both semi-conducting materials. Do you understand? Now, those elements, we call them metalloids. No, we will do specific things. This is just in general. You need to know the term metalloids. If I ask you what is a metalloid, then it's an element that lies on or near the step that shows properties of both metals and non-metals. Okay. In general, when we classify something, if it has mostly metallic properties, then we will classify it as a metal. But for example, tin, we get one of the crystalline structures of tin that looks like not a metal at all. It looks like a non-metal.
Oh,
all right.
So there's an
yeah. Yes, both sides, up and down. The ones that touch the step. All right. Yeah.
So we just say on or near of the touch?
On or near the step. It's fine. All right. Now, the next part in your textbooks, they refer to group 1 and group 2, the alkali and the alkali earth metals. People, a couple of things that we need to know. When they form salts, they are usually white salts, colorless compounds. Okay? What is the properties of the transition metals? They form colored compounds because copper salts are blue, zinc is white, iron salts are red or green, etc. Okay. They are mostly the group 1 and 2 metals when they form salts. Those salts are usually soluble in water. All right. And we find that the reactivity of the group 1 metals increases from top to bottom. Group 2 also increases from top to bottom.
So the honors is
more reactive, yes. We don't work with them. It is just elements that there is, but many of them are made in laboratories. They exist for a short period of time because they're radioactive and they disintegrate or they break down, undergo decay. They don't make uranium, they mine it, but some of the others. Yeah, they enrich uranium to get a specific isotope of uranium that they need for nuclear reactions and stuff like that. Okay. Yeah, we don't need to know them. Just leave it, please. Okay. The transition metals then, in the next section, if you check there, they say the metals are not as dense as the well-known ones. So group 1 and 2 metals are not as dense as the well-known ones. So then the transition metals, just in general, they form a block of metals. They are hard, they are strong. They usually have high densities, hard, strong, dense materials. They form colored compounds. And then they say the metals become less reactive from left to right. So the transition metals that lie on the left-hand side of the block of transition metals, they are slightly more reactive than those that lie on the right. But it's not like a fixed golden rule. Okay. But if you do look, you'll see elements like silver and gold and platinum. They lie here on the right-hand side. Okay. And iron that we know will rust, for example, lies more to the left-hand side of the periodic table. That's just general sort of tendencies. The whole periodic table, as you work, except for the group 8 elements, we find then that group 7 and group 1 are fairly reactive. Group 2 is less reactive than group 1, so group 6 is less reactive than group 7. So there's a general tendencies of
From the inside.
Yes, yes. Okay. Then,
It has to do with the electrons in the outer shell.
yeah, mostly.
Is it that the same way with the transition metals as well?
Yes, well, not from inside out, but from left to right.
Yes, yes.
All right. The transition metals then, just very simply, this means that the least reactive ones, such as gold, are found on the bottom right over there. So the reactivity decreases from left to right and from top to bottom.
Okay, now,
All right.
Mercury. Mercury is a liquid, but it's very not. It's almost not reactive.
Yeah.
But gold is more reactive than
Yeah, but that's
mercury
just
in the
general
solid.
tendencies. It's just it's inherent properties of the elements. Okay. So the B metals, they are very often, I'll put in brackets there, the metalloids, because they all touch the step, not all of them, but most of them do, all right? So we don't worry too much about the B metals. They just say, yeah,
Bromine and silicon and those can also be classified as a metalloid.
no, not bromine, silicon, boron, yes.
Yeah, because it also touches the
Yeah.
step. So a metalloid is touching the step. It doesn't need to be a metal too.
Okay. The non-metals on the right-hand side above the step, well, we know they are dull, they are not shiny, they are not workable. The non-metals, you should know hydrogen, nitrogen, oxygen, fluorine, chlorine are gases together with group 8. That's nothing new, all right? You need to know that in the non-metals there are some diatomic elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, or diatomic astatine as well, but we don't work with it very much, all right? So the non-metals, they have one thing in common, and that is that they are non-metals. When they bond with each other, they form covalent bonds. When they bond with the metals, they form ionic bonds. Just general tendencies. No? Then the group 8 elements, the noble gases or inert gases, helium, neon, argon, krypton, xenon, radon, they are unreactive. They have filled outer shells, so they don't react. We use them in places where we need inert atmospheres. Yeah, for example, within a light bulb. I watched a YouTube video the other day where they switch on a light bulb. They've broken the glass around the bulb and they switch it on. It burns for 2 seconds and it goes out because of the oxygen in the air. And the inert atmosphere prevents the metal from oxidizing. Now, it's not melting, it oxidizes, it rusts, and then it becomes brittle and it breaks. Okay, and it doesn't conduct as well. So, yeah. Yeah. Yeah, it will stop working, yes. All right. They work slightly different to the filament light bulbs. Okay. Yeah. All right. Then the lanthanides and the actinides, you can just put a bracket around it. We don't do anything. Just know uranium is the most important one because it's used as fuel in power reactors, etc. And it's mined in Namibia. When we do the extraction processes, we'll have a look at uranium again. Then they go and specifically look at group 1, the alkali metals. In other words, lithium, sodium, potassium, rubidium, cesium, francium. And we find that their boiling points decrease. The bottom ones are, if it's a hot day, liquids at room temperature. All right. Their melting and boiling points decrease as we go down. Their densities tend to increase as you go down the group. Just general group 1 metals. Okay? The alkali metals. Cesium is classified as a solid, but if it's warm enough, room temperature, melting point is around about 24. Here by us it will usually be in the form of a liquid. You don't need to go and remember melting and boiling points. It's just general tendencies that you must know of. Yes? Yes. Yeah.
Cesium is 29, my boiling point is 6.
Yes. Because you require more energy to boil. Well, it's got to do with the forces. Yeah. It's just, it's inherent properties. Yeah, that's a slight discrepancy or an aberration if you want to look at it like that. No. Sometimes we find that as the extra shell is added, the nuclei are further apart, so the forces holding the particles are acting over greater distances. But sometimes it's got to do with the extra shell has an extra positive charge to it. So these things all sort of play a role. Okay, so just in general, the general tendency is for boiling points to decrease, melting points to decrease, and density to increase. Okay. The group 1 metals in general are very reactive. If I had sodium and potassium in the laboratory, I would store them under an oily liquid or within an oily liquid. The simple reason for that is sodium and potassium are so reactive that if I had them not covered by an oily substance, they will react with the oxygen and the water vapor in the air. And here by us in the summer, there's lots of water vapor in the air. The potassium will start burning. The sodium will corrode. It will become hot. There is a chance of it starting to burn depending on how much moisture there is in the atmosphere. All right. So they are very reactive. We store them under like paraffin or any oily substance. You can't store them under water because they react with water violently. So they float on the surface, they run on the surface, they melt and they burn. Okay, potassium burns with a nice purple flame. When it runs on the surface, you can see the little purple flame above it. Sodium, you cannot see that it is burning, but it melts. You can see it melts into a little droplet that runs on the surface of the water, and eventually it disappears because it forms sodium hydroxide that goes into solution. It leaves a little milky trail on the surface of the liquid. All right, we can check and see maybe if we've got some time somewhere along the line in a double period for a video on these metals. Okay. The table 3.3 in your textbooks on page 42. There they have a look at the chemical properties of the alkali metals. Now, they all react with water. If you read the first three, lithium, sodium, and potassium reacts with cold water. Sodium reacts vigorously with cold water. Potassium reacts violently with cold water. The increase in reactivity as you go down the group, they all react with cold water and they will form the hydroxide. So it will form lithium hydroxide, sodium hydroxide, potassium hydroxide. Now, if I have, let's say, sodium and it reacts with water, H2O, it is going to form sodium hydroxide. This is water soluble plus what? Yes, hydrogen gas. All right. And you would be able to catch up the hydrogen gas and you can test the hydrogen gas. How do I test hydrogen? Burning splint, whistling or popping sound. All right. So all of the group 1 metals will react similarly with water, as if it was an acid. You get a salt plus hydrogen gas. Then, if we go and have a look at their reactions with oxygen, they all react with oxygen. Yes, all sodium group 1 and 2 metal salts, most of them are soluble, so if you have to guess, you could guess them as soluble. Yeah. Okay. There are singular exceptions. I can give you the list. No. The grade 10s do the solubility rules. Yeah. All right. Then the reaction with oxygen, they will all react with oxygen. They will burn, and the product will be a white substance. So when any of these metals, let's take lithium, if lithium reacts with oxygen, it is going to form lithium oxide. Okay? Yes. And lithium oxide is a white solid. This is water soluble. Okay, but they all form white salt, so that stuff is white, that stuff is white. Okay, so that is the reaction with oxygen. They also like reacting with the group 7 elements. They are very reactive. Group 7 elements are very reactive. So let's take potassium with iodine, and it will form potassium iodide. All right, very willingly. It's actually an oxidation reduction reaction, very similar to the combustion reaction chemically. Okay. Yeah? It is the permanganate part that is the active part. You could have just as well have had sodium permanganate or whatever. Yes, but it's in the form of a salt. It's like sodium metal. It burns when exposed to air or water. But sodium hydroxide is a stable salt, or sodium chloride is a salt which is stable. Remember, the properties differ when they form compounds. Okay. So they like reacting with the group 7 elements and they form salts. The flame color, that is not part of your syllabus. The grade 10s do the flame color. Lithium is red.
Sorry, is the salt white?
Yes, they are all white salts. The flame color test, they just dip a piece of wire into the salt and they hold it in a flame, and the flame color changes depending on what metal we have. All right, so, but you don't have to worry about that. You don't do that. Lithium is red, sodium is yellow, potassium is purple. Yes, the symbol, lithium, sodium, potassium, all +1 metals because they lose their outer shell electron. And then the salts, you will see they are all white crystalline solids which are soluble in water. The sodium salts, or white crystalline solids which are soluble in water. The potassium salts, white crystalline solids which are soluble in water. Group 1 and 2 metals form white salts, and they are usually soluble. Some of the hydroxides of group 2 metals are insoluble. Okay, but in general they form soluble substances. No, you don't need to know the flame test. Then they've got there in the bottom of page 42 the reaction with a metal and water. What they go and do there in the picture is they take sodium metal and they wrap wire around it. The reason why they do that is they want the sodium to sink. If I add sodium metal to water, it's going to float on the surface. And then you cannot see the bubbles for the hydrogen gas forming. So what they're going to do is they go and wrap a piece of sodium just in a piece of metal wire. And they put it into the water, and then you can see bubbles forming. And those bubbles are bubbles of hydrogen gas, because we said over here, when they react with water, they form hydrogen gas. Okay. The reaction of the metal with water, this is an alkaline substance. pH will be greater than 7. Okay. You can see as the sodium runs on the surface, it leaves a milky trail that sort of disappears into the water. And that is the sodium hydroxide that has been formed that dissolves. Okay. Group 1 compounds, the group 1 metals, when they form compounds with the non-metals, they are all ionic. Okay. Yeah, that's just simple. Yeah, it's just information. They say all group 1 compounds are colorless crystalline solids which are soluble in water. Okay.
Ionic.
Yeah. Soluble salts. Yes. Colorless and water soluble. The reactivity of group 1, we've already said it increases down the group. All right, then in your books they jump to group 4. Now group 4 is carbon, silicon, germanium, etc. They have in common, they actually form a unique group because the first 2 are non-metals, the last 3 are metals, but many of them are actually metalloid in their properties. In general, they have got 4 electrons in their outer shell, so depending on what they react with, they can either lose or gain 4 electrons. All right, we don't work too much with them. We will work with carbon when we do organic compounds and when we do carbon dioxide and carbon monoxide. All right. They say the central group of the periodic table shows very clearly the increase in metallic characteristics down the group. So they start off with non-metals, metalloids, metals as you go down the group. That is what that sort of sentence means. They say carbon and silicon are non-metals, and tin and lead are metals, yet one form of carbon, graphite, will conduct, and tin exists in both a metallic form and a grey non-metallic form. Okay, it looks like a, well, crystalline substance. Carbon is very unique. It forms 4 covalent, or it can form 4 bonds. And this makes carbon very versatile. Okay? Depending on how much energy is available and the temperatures during which this process occurs, carbon tends to burn when it reacts with oxygen, and it forms carbon dioxide. But carbon itself also very often undergoes sublimation, and that is why when you have a flame in the laboratory and you don't set the Bunsen burner to have a blue flame, you put something on. If the flame is yellow and smoky, then it's full of carbon on the outside. This is the carbon from the hydrocarbon fuel that has undergone sublimation. It forms a single little atom of carbon, which they sort of collect together, and it condenses, or it resublimates on the surface of the object, making it all sooty and black. All right. The fact that carbon can form 4 bonds makes that it can have various shapes. We know about the different crystalline structures of carbon, diamonds and graphite. And then there's another one, they talk about fullerene, but we'll have a look at them when we get to that. They say silicon has properties of both metals and non-metals. All right? It is a grey solid that looks like a non-metal, but it conducts electricity better than a non-metal does in general. We call it a semiconductor. Now, semiconductors, the difference between a semiconductor and a normal conductor is, for a semiconductor to be able to conduct, it needs a minimum potential difference across its ends. If you have more than that, then it will conduct. But if your potential difference is less than that, then it doesn't conduct. Okay, germanium works like that. I can't remember exactly. I think it is 1.6 volt and 2 volt or something like that. Yes, if I have less than that, it does not allow charge through. But if I have more than that, it does. Okay. The group 7 elements, they jump to after that one then. The group 7 elements, we call them the halogens. They are all non-metals: fluorine, chlorine, bromine, iodine. Fluorine is a yellow gas. Chlorine is a green gas. Bromine is a red-brown liquid. And iodine is a shiny, dark purple crystal. It's almost black. All right. Iodine tends to undergo sublimation when you heat it up. It doesn't melt. Bromine is actually very poisonous. It's carcinogenic. It can cause cancer. So in general, in school laboratories, we do not work with bromine. When you do buy bromine, you can't buy a bottle full. It's usually in little glass ampules that you have to break open, and then there'll be a milliliter or 2 in the little ampule. But you need to work with it under special conditions where you have a fume cupboard. You should not breathe in the fumes of bromine. And because it is a liquid, liquids tend to evaporate. Okay, so we don't work with bromine. We will work with salts of bromine, potassium bromide, for example, but we won't work with bromine as a liquid in the school laboratory. They say the group 7 elements, all of them are poisonous, but they are also very often micronutrients. For example, iodine. Your body needs iodine. It helps to regulate the function of the thyroid gland. But in too large amounts, it is poisonous. That is why they can chlorinate the water, because in small amounts, your body can cope with the chlorine. that in large amounts it is poisonous. Okay. So in general, the halogens are all poisonous. Bromine especially is a carcinogen. Okay, it causes cancer.